Hey everyone, welcome to Morehouse Metrology Matters. Today I have Greg Cenker with me, and we're just going to have a conversation. We can start with I was just listening to Tool this morning, Greg, and I hadn't listened to Tool for a while. Is that one of the bands that you like there with all your guitars in the
Oh,
background?
of course it is. Of course it is. Adam Jones has got an incredible guitar tone.
The Enema is the album, like from start to finish. I was just thinking about all the awesome albums that are out there, and we've been working on some documents together. And I've been listening to a lot of AC/DC Powerage, a lot of Ozzy Osbourne, Blizzard of Oz. And I'm just blown away by Ozzy's first album, right, with Randy Rhoads.
Oh, yeah. It's funny you mentioned that. When I was on the plane coming back from the NCSLI Tech Exchange, that's the album I was listening to. And
No,
I was also
really,
yeah, I was
yeah.
listening to that, and I was listening to Ozzy Osbourne live, the only live recording that they released with Randy Rhoads playing.
Oh, the tribute because they had Speak of the Devil, but that was other people.
Yeah,
And
that was
then yeah, the
Brad
tribute
Gillis.
album. So
Yeah.
the deluxe edition of Blizzard of Oz, which I'm sure all the metrology people out there are loving us talking about this. But like I said, this is kind of a glimpse on Craig and I's discussions and how we talk. They have some live versions with Randy Rhoads as well, and just the sheer volume of songs. And that album didn't do super well, but Mr. Crowley's on there, Crazy Train's on there, Goodbye to Romance is on there, No Bone Movies is on there. Randy Rhoads did this little thing called D, this like classical guitar thing. Yeah, it's just I just rediscovering things that you might have listened to from your childhood is really cool. And how many of these albums, like the people today, they don't listen start to finish. I mean, the only way I knew how to listen to an album was probably the first 11 songs, and then by song 12, I was off to running, jacked up or running to go do something. So I usually miss the last song of the album for some reason or another, turning the car off to go to the mall or whatnot.
So interesting story about Mr. Crowley. So Zach Wild, Ozzy's guitarist for I don't know how many years, they were having a get together at his house, and Zach gave him a framed poster, and he said, Ozzy said, "Well, who is that?" He said, "Come on, Oz." He goes, "You're pulling my leg." He said, "You know who this is." He says, "Who is it?" And he goes, "You've been singing about this guy for 20 years." And he says, "It's Aleister Crowley." He goes, "Oh, so that's what he looks like."
He's just somebody. I don't know if he wrote it or not, though. It's interesting the whole how we tie Ozzy Osbourne to metrology. I don't know the guitar tones and everything else. If you're on YouTube and look at this, you can see Greg's impressive collection of guitars, and behind me you can see the formula for TUR, also known as in JCGM 106 Measurement Capability Index. And for those that do not know Greg, there's a Metrology Today podcast that where we Greg talks all about his history and his life. Just a brief overview. How many years in metrology, Greg?
I really cringe when I say this, but about 40 years now.
40 years. And you
Yeah,
started when you
I got
were
into
you started
metrology.
when you were five, so that's
Yeah, 5 or 6.
So no, today's a good thing because you and I have done so many different collaborations and stuff, and the one that we're super passionate out right now, I'd say we're always passionate about something or someone's doing something wrong or we think we can save someone money is this TUR, and how it's used and how companies could use it to benefit themselves if they know what they're talking about.
Right.
And that's a big if because we've written the decision rules guidance, right? We talk about TUR in relation to specific risk, which I get in trouble for. There's certain people that do not like any discussion of TUR associated with specific risk because there's a lot of people that say TUR is only used when you talk about global risk, which gives you two probability density functions. One's for your what you're measuring and one for your process generally.
Well, somebody's going to have to really explain that one to me because whether you're utilizing specific risk or global risk, you still have a measurement uncertainty that's associated with either form of guard banding or conformance testing. So somebody needs to explain to me why it wouldn't apply to specific risk, but it would apply to global when you still are calculating a test uncertainty ratio. That
Well,
makes no
yeah.
sense.
Yeah, it's a formula, right? We can
Right.
all go, people on there, hopefully there's some people listening, maybe they can solve it for us, but ANSI Z540.3 in the handbook does it just says about the 2% rule. And it said when means other than, you can't calculate the PFA of 2%, something like to those, I'm summarizing generally, that you can use other methods. And TUR is such a butchered term that when you and I sat down with Scott Mims, who worked for NASA for eons, written several papers, Scott just said, "Hey, stop talking about TUR. It's butchered. If you want to talk about what we really want to get to, it's measurement capability index, because that's
Right.
what's in JCGM 106. It's the same formula for TUR. It's just JCGM 106, I believe, is always referring to measurement capability index using a more of global risk models and their plots.
Right. Right. And and it's going to be slow to adapt to the metrology community because everybody's so used to TUR. But to your point, it's been butchered so much and misunderstood and inappropriately used. So by switching to a measurement capability metric, it's going to take some time.
Yeah, and
But it is a better terminal. It's better terminology and it's more concise and precise.
right, because people confuse TUR with TAR. So for
Yes,
those
they
out there,
do.
TAR is just accuracy. It's the specified accuracy of the device versus the specified accuracy of the reference. Some people have rewritten this, right, to it's the your specific accuracy tolerance limits of the device divided by the measurement uncertainty. We've seen that, so that's butchered. We've seen TUR be butchered with just accuracy divided by measurement, the reference uncertainty, no contribution, no additional contributions for the UUT, such as like resolution of the unit under test, repeatability of that unit under test, temperature factors, and everything else. And you can find the definition of TUR, a complete definition of TUR in the ANSI Z540.3 handbook, which basically says that denominator is going to include a lot of stuff. It's more than just the measurement uncertainty of your process. It's going to include that device or unit, the device that you're testing or unit under test.
Right.
So
So,
that
so
being said, let's dive into what TUR is, and then we'll go with what you're working on.
okay. So TUR is nothing more than the nothing more. That's an understatement. It's the span of the tolerance of the unit under test that you are testing, and it's going to have a lot of contributors. You're going to have the inherited uncertainty, you're going to have the resolution, you're going to have repeatability, you're going to have environmental contributors, you're going to have maybe a coefficient of expansion that's going to
Mm-hmm.
be included in that. There's just so many things that need to be taken into account. One of the examples that I have, Henry and I worked on, was a simple kitchen scale. And the short of it is you have a scale that has a resolution of 1 gram, and that's also the tolerance is 1 gram. So taking out the uncertainty of the masses that I use to just kind of verify this kitchen scale, you have the resolution divided by root 12 squared, and we just put a repeatability number of 1 gram and a reproducibility number of 1 gram, and all of a sudden that plus or minus 1 gram accuracy now is truly 2.88 because you have all the uncertainty components in there. So you might be, and when you make a statement of conformance, you could say that maybe you measured it at 4,000 grams, and the tolerance is 399 to 4,001 plus or minus 2.88 grams. So I mean, when you look at that, it doesn't make sense, but that's really the true way of expressing it because that is including all the uncertainty components.
Yeah, so you have simplified, you have the UUT accuracy tolerance, and that you divide it by a whole bunch of stuff. Your measurement process
Right.
uncertainty, your calibration and measurement capability. Often the resolution of the UUTs in there. There's some rules between if you have repeatability and repeatability is high, maybe you don't put the resolution in because the repeatability is going to detect it. Most of the time, you put the resolution of the UUT in there. You put the environmental conditions, the temperature specs, all kinds of other things, and the handbook really has a good definition of TUR of. In fact, let me just read it. The 95% expanded uncertainty of the measurement process used for calibration following the calibration procedure is used to calculate TUR. The value of uncertainty estimate reflects the results that are reasonably expected from using the approved procedure to calibrate the MNTE. Therefore, the estimate includes all components of error that influence the calibration measurement results, including the influence of the item being calibrated, except for the bias of the MNTE, the calibration process error, temporary and non-correctable influence incurred during calibration, such as repeatability, resolution, error in the instrument source, operator error, error in correction factors, environmental influences. Now, how many people have all that in their denominator when they do this?
Not nearly enough. We see it all the time. I see it when I go to other laboratories, and most often than not, they are included incorrectly. They have incorrect numbers that are in the denominator, and there. What really makes me uh, puzzled in all of this is the amount of education that we have now, all the guidance documentation that we have. We have YouTube videos, we have NCSLI webinars, we have NCSLI conferences, we have MSC
Yep.
conferences, we have free papers available. There is far more information available now than when I was up and coming in the metrology industry. But as a whole, people are doing it incorrectly, even with all this information. And I'm
Mhm.
quite frankly, I'm puzzled by it. I don't understand.
And
Um,
people are generally confused by it too, because it's just was the understanding of it is you had TAR, which is an easy concept in the 50s, and then you switched to TUR, and it wasn't really fully explained until that handbook.3 came out, and not everybody has access to the ANSI Z540 handbook.3.
right.
Right. And before that handbook, it was even more confusing. And then since then, it's been butchered because people try to push their own agendas on things. And that's our understanding of why JCGM just said, hey, measurement capability index, TUR's defined, been butchered, people confuse it with TUR and everything else. Let's just take that definition of TUR and say this is measurement capability index, which includes our process as well as the contributors for the unit under test.
Right. And let's go back a little bit. Let's revisit that 1955 document. When you actually read that document and it is talking about test accuracy ratios, there's a
Yep.
caveat in there that everybody seems to miss. And that caveat is the assumption that the unit under test and your reference standards are all at 95% in the period reliability. That is the
Hmm.
caveat that's missing that no one wants to talk about. So when you
Now,
when you
you made
talk
it harder, Greg. What's harder?
but Jerry was ultimately talking about TUR, but he was talking about that in terms of reliability, which was in that paper, but that got completely glossed over the years. Um, to go
It's
back
hard.
and yeah, to go back and read what Jerry actually did in 1955. First off, it was an outstanding piece of work considering the complexity of how to calculate um, probability of false accept, probability of false reject. I mean, these guys were doing it with slide rules. And they came up with a very, very easy patch to be able to do this with test accuracy ratios. But like I said, it was under the assumption that both the unit under test and your reference standard were performing at 95% and the period reliability or greater. And
So what that basically means is from one calibration to the next, it was holding specifications.
correct.
Okay, so that's what when we start talking about end of period reliability, there's so many means to calculate this. There's different. We can talk about guard bandit and all that stuff, but really, what was the summation is that hey, if I had 20 items of model XYZ, 19 of them would maintain, and my calibration frequency was 1 year. 19 of those 20 items would maintain its accuracy specification, giving me 95% end of
Right.
period reliability. It's simplified to the, you know.
Right. That's really what it is.
So, and Jerry knew that, and then he originally came up with this and did like a 3-to-1, and then said, "Oh, we need a buffer and everything else." And they would draw risk curves, and you can read his paper, and also is it test accuracy limits was the at the same time a little bit before that Sandia, Wisen, and Clark were working on this other one
Yeah.
or test specification limits. Two papers that are just there's actually three in there because there was the Grubbs paper, there's Jerry Hayes's paper, and then there's the Wisen Clark paper from Sandia
Right.
Labs, and they're all talking about the same thing. And this brings us to why is this important? Like people listen to us jabber and talk and come through and say, "Oh, I kind of get it. You guys are might simplify this a little bit. I kind of get it, though. Yet I really don't get it anymore. I really don't get it." It's because we start throwing in a lot of different stuff. So if we can simplify this to the basics, right? Test uncertainty ratio is basically, as you said, the span of the UUT tolerance, and then that gets divided by the 95, typically 95%, depending on what somebody wants, 95%, two times the expanded 95% expanded uncertainty of the measurement process, which includes all that other stuff. And then end of period reliability basically assumes that you set your calibration interval so a certain percentage of those devices stay in tolerance. Those are two key things that we talk about. Then we start talking about these papers, these test error limits and the other ones. And why does this matter? Because this is what we're passionate about now. Like if people do this right, and they calculate everything right, what's the benefit? Why should I do it?
Right. Well, first off, the reason why you should do it is because it's when you get right down to the cost of it, the cost savings of why you should do it correctly are enormous. So when I was at the tech exchange, one of the topics that I brought up was a specific OEM that was building a component of a product. And this component was very critical to the overall reliability of the product. Well, they also had another requirement. The requirement that they had was that they wanted no more than 54 parts per million. In other words, 54 units out of a million that reached the consumer's hand failed. So their risk appetite was very, very small. When I originally looked at this, what happened was they were at a test uncertainty ratio of 2.5 to 1. So based on the numbers that they had and the risk appetite that they had, I suggested some other equipment. Well, they didn't like the suggestion in terms of what they perceived to be an upfront cost and investment because they had several facilities that were manufacturing this product. So what I had done is I asked a few questions, and the questions that I asked were, okay, well, if these items fail on the production line, what happens to them? Do you retest them? Do you send them to a secondary test point or checkpoint? Do you scrap them? What happens to them? They said, we just scrap them. And I said, okay, so how much do these cost to manufacture? And they told me, and just for example, I said, well, they're $6.90 to manufacture this particular part. They planned on manufacturing over a million of these parts every quarter. And I don't recall how many factories that they had churning them out, but I just did the math on 1 million parts per quarter. So the cost for a false reject was $6.90, meaning that it failed, they throw it away. The cost for a false accept, meaning it reached the consumer's hands, and the consumer is now going to have this device serviced. So now we're talking logistics. We're talking about delivering more spares to any one of the outlets where they sell these items to be able to service them. Well, that cost for each service item was $85 per unit that they had serviced. So running through the mathematics and these risk models and using the TUR and everything else, I calculated that every quarter it's going to cost them $2.8 million in false rejects because of their low TURs. Every quarter, $2.8 million. Well, they rectified that and they decided when I put it in dollars and cents, then that made management kind of pick up their ears a little bit and say, well, you know what, maybe we ought to invest in better equipment. So they went from a TUR to a 24-1. They went way overboard TUR.
So they were getting their 50, less than 54. Well, theoretically, they're getting, on paper, they're getting their less than 54 out of a million.
Right. On paper, it was 54 out of a million. But since they ramped it up and got much, much better test equipment on their production line, where they had an increased test uncertainty ratio of 24 point something to 1, their cost went from $2.8 million a quarter to $93,000 a quarter for false rejects.
Yeah, and the calculation that they wanted to maintain was less than 45, or less than roughly 4,600, right? 85 times 54, about, $4,600.
Right.
Right. So even though all the numbers showed that they were going to get there with their 20 some to 1 TUR, still people make mistakes and everything else. So when we talk about things on paper, numbers are a good what would we say, an acid test, so to speak, or what's a better word for that, Greg?
Well, the test that we do on paper, the reason that we do that is to put confidence that you're buying the right equipment, you're minimizing the risk. Then that has absolutely nothing to do with your quality in terms of what you're building. So just we want to take what you're building out of the equation and just focus on, am I buying the right equipment the first time to be able to reach a high level of reliability in the product that I'm shipping? So that's what we're doing. We're typically taking the unit under test out of the equation, and we're focusing on what's my appetite for risk and what's it going to cost me if I don't do this.
The saying I like is what starts right ends right here.
Right.
And what you're doing is essentially you're starting with equipment that has potential, big word there, right? Potential to meet your goals. You're probably not always going to meet your goals because things happen, right? Systems break down, production says keep running with bad temperature, keep doing this, push product, do that. And you can get better and better. There's a lot of companies out there that have the goals that say, hey, we went from 2.8 to 93,000. Can we get that down to 20,000? Can we get that? And then keep trying and trying. Eventually you get to a point of no return where it's just, hey, just focus on continuous improvement and culture and doing more of the right things. And you're probably going to eat some scrap.
Right. But the scrap rate that they had, that was acceptable to them. I mean, $4,600 false accept risk was a lot better than $2.8 million. So that was highly acceptable to be able to do that.
It's funny because people, they often say people just buy on emotion, and then they come back and they try to justify it with numbers. Right. So if I buy an instrument that only gives me a TUR of 2 to 1, I'm going to come back to management and say, the sales guy, these are all the cool things it does. We have 50 locations. It's going to save us overall, going to save us $500,000 for these 50 locations. It's going to look good. the depreciation schedule, all these other things that you start factoring into this equipment is going to look pretty good, and we're going to be afforded. And the shareholders, the almighty shareholders, you know where I am on this, because yeah, that's my little tangent on shareholders. Are there some companies that are so budget conscious that if they have a payback of 2 years, they're not allowed to do it, right? It has to be 18 months or it has to be 1 year. And they can't see that if I spend a lot of money now, I in 2 years will be making double that amount because be rejecting a lot less. They're under this. But anyway, I regress on this. But going back to this, this is where it's a big thing because industry often does this. Somebody goes out there and they look at these specification sheets and they just assume, and a salesperson says this is good enough to measure this, or the guy or gal that's knocking on their door comes in with their line items, and all of a sudden they have an answer for you. And the person that's in production is not a metrologist, and they're trusting the people that are trying to sell to them, which frankly probably are not metrologists either.
Right, and that's been my struggle my entire career. And even when I went to the NCSLI Tech Exchange, that is still an ongoing struggle where you have lab managers that are asked to calibrate something that production ended up purchasing, and either they can't calibrate it or it doesn't really truly meet their needs. And the simple question is, why don't you guys talk to us before you purchase these things? That almost never happens. And I don't understand that. I mean, I saw it firsthand when I worked at Southern California Edison and other companies as well, where you have people that are on the production floor buying test equipment based on some sales pitch, thinking that it's new, it's better, it's shiny, and only to find out we can't calibrate it. When I was working at Northrop Grumman, there was a program that wanted a very specific impedance analyzer, and it wasn't that special in terms of what it was able to measure. We had other options that were available, but the customer, the process owner, wanted this particular piece of equipment. So, and they wanted to be able to maintain it. So within a 5-year period, this one piece of equipment that cost $19,500 in 5 years was going to cost over $265,000 because of the ancillary equipment that had to be purchased, how it had to be calibrated. The ancillary equipment had to go to NIST every other year for a 5-year period. So it went to NIST for three times, and then it was sent back to the vendor. And after I got all the equipment purchased for this particular project, then the project just went away. They all of a sudden didn't need it anymore. But we're talking about one piece of equipment, one that was $265,000 a year to maintain, where if they would have purchased something that we were already able to calibrate and maintain, that cost over 5 years was less than $4,000.
It's crazy, and it all happens, and we all
It
make
does.
mistakes. So like, it's admitting the other problem that we see, or at least I've noticed, is somebody buys this and then they double down with it instead of just scrapping it and saying, "Look, I just spent 200, what was it,
$5,000.
$265,000. I spent this, and it's just gonna keep bleeding. My hole is just getting deeper. Why don't I just stop digging and buy the right equipment and get myself out of the hole? Maybe now I have a 3-year return if I have to lump everything together. You know what I mean? People
Yeah.
that calculate this, you say, oh no, but if I stop right now and then I calculate, I buy the right equipment, maybe I can be profitable in 3 years from my mistake. But if you keep going down the wrong path, what happens to the company? You just keep burning. So many people just burn money, right? And
And,
we all do it. Like,
yep.
look at there are people. Oh, listen, look at in your refrigerator. Greg, I know you probably do this too. how many things you forget about? Like you buy a mixed salad or something, and then you end up going out to dinner, and then 5 days later, you're like,
Throw it
oh,
out.
that's in the back of the fridge, and now it's no longer good, and you throw it out. So
Right.
we waste. I hate when we do that. My wife yells at me like it's past expiration. I'm like, I'm eating it. It's like it's gonna take the one time for me to get really sick for me to stop doing this, and that's what I tell her, and I'm like, yeah. So. Do I need to eat it? No, I just feel guilty if we waste it. If it's moldy and crusty or wilted, then I won't eat it. But if it still looks good, I'll, take a bite and be like, "Oh, okay, I'll eat it. I'll put some wasabi peas in
That's
it."
my litmus test. I'll taste it, past its expiration date. Yep, tastes
Yeah.
fine. I'm eating it.
Yeah, and there's some that go over. Though it's just we spend money, ridiculous amounts of money in business and everywhere that we don't need to spend. We all know that. And then we get cheap when we do need to spend it. And that's the other thing that's so interesting with the way our dynamics and our brains are wired, right? Like, okay, I need this, the example we write in the decision that I have behind me here that you can kind of see we took the JCGM resistance example and we go through, like, if I buy like a really cheap meter, I'm rejecting this. But if I buy a really expensive meter, I'm rejecting this amount. And we said production. So from the expensive meter that someone thinks they could do well with, which was about 1.44 to 1, just an instrument that's a little bit better than what you're testing. It was like 23.97% versus if we bought a really good meter, it was the rejection likely production rejection rate went down to 0.03%. And the difference in cost was like 16 grand. So you factor in how many things are you going to reject? What is the rework level? What happens to stuff when you reject it? And these companies just, I've been to lean classes, I've been to Six Sigma classes. A lot of the owners just say, "Oh, we'll sell that scrap elsewhere, or we'll turn it into something else." But it's incredibly expensive.
Right, it is. And if you just put, I mean, the old adage is true. An ounce of prevention is worth a pound of cure. And if you
Yeah.
just do some homework up front, what am I measuring? What am I building? What's the spec? What's the test tolerance? Engineering may not have all the correct answers when they give you the specifications, but once you have them, at least make an informed decision about what you need to make that happen. And by being informed and knowing what you need to make that happen, you have a less likely probability of somebody pointing a finger at you saying, well, you recommended the wrong test equipment. No, actually, I did. Matter of fact, if you use this, theoretically, your scrap rate should be very, very low. So you have a problem in your production, or you misspec this item, or whatever the case may be.
Mhm.
But that's what we try to do up front, is take the unit under test out of it and say, okay, what are we building? What are we going to test? What do we need?
And what's our risk level, right?
And
If I
what
just need to, yeah,
what's
like dumb stuff. Like I could buy a multimeter, not for, I don't want to say names of people, but I could buy a pretty cheap multimeter, and I could have a lot of confidence that there's power to my outlet, right? If it reads, I plug it into my home outlet and it reads 119. Do I care?
no.
Maybe I don't. Maybe I care nothing of it. I just want to know that power is coming to that outlet. So that's a different level of risk in in my point of view that companies need to analyze, and that anybody needs to analyze, right?
Right.
Because if I'm just using something for a simple check, that's a lot different than a rejection of a part. It's just okay, do I have power coming to the outlet? Yes. Oh, maybe I better shut the switch off in the breaker to go work on my outlet or do something like that. Completely different than I need to pass a large quantity of resistors, and I'm not going to use this handheld multimeter that I'm going to use on my outlet at home, am I? I mean,
No.
no, it doesn't make any sense. And you start looking at how good you need to be, the specification of what you're testing, and people don't put that together. They just go out. I mean, why on the upfront research is it so to the point where people do not want to, many people, not all, do not want to really educate themselves?
Right. And they stay in the dark, and it's almost willfully that
Yeah.
they stay in the dark about this. And like, well, no. And to your point, behind you on your screen, you've got the low buck version of a meter. Yeah,
Yeah.
and that's what people see. So they
Yeah.
see the low buck cost, and they're like, you know what, I'm buying this. That's fine. but they
Yep.
don't realize the ramifications of what that's going to do to their end product. Where if they just spent a little bit more, in this case, if they just spent, you know, twice that amount, well, three times that amount for
Well, yeah,
13,000.
it goes, yeah, if they, depending what they want to get to, right? Yeah.
Right, right. It depends on their level of risk, but I mean, the cost is always the driver, and managers really want to know two things. They want to know how much is this going to cost, and how long is it going to take. Well, you can't when you're talking about stuff like this, you can't get into the minutia because you're going to lose them, and you're going to start sounding like Charlie Brown's teacher to them.
Yep.
You have
Womp
to put
womp.
it.
Womp
Yep.
womp
You have to put it
womp.
in terms that they understand, which is okay, you could buy this cheap equipment, but your overall cost over time, over a quarter, over a 6 months, over a year, whatever the case may be, is going to be X. So if
Oh,
you buy
yeah.
this, this is what it's going to be. But if you spend this much money, then, and this is the risk appetite you have, then this is what likely is going to be driving your costs. So,
Assuming you know how to use it correctly. I mean,
well,
there's a
there's that.
lot of assumptions in here because someone buys the right equipment and then said, "Hey, that Greg and Henry said this, and it's I'm costing me $1 million." No, theoretically you probably need some training. If you're
Right.
using, yeah, I mean, test leads matter. There's all these other things that matter. Environmental conditions may matter depending on how what you're measuring and what the tolerance of what you're measuring is. There's so many things that you get into, and
Okay,
that's
so
what, yeah,
to your point on that, you can have the best test equipment in the world, but unless you have somebody that understands the process and what's going on, it's not going to do you any good. Now, I'm not going to mention any names here of a manufacturer, but kudos to the person that caught this error. So I was running the primary lab at Southern California Edison, and I had all of my resistors under SPC. Well, the person that was in that came in behind me after they were trained, they kept complaining that the bridge was giving them the answer and the resistance values, but they were wrong. They were off. Their SPC shifted. I went in there and I did an exhaustive study on it. I went from literally 1 ohm all the way up to 1 gig, and then reverse bootstrap from 1 gig all the way back down to 1 ohm. And I got to where the 1 ohm was that was within my uncertainty. I'm like, I don't understand what the problem is, because if there was a problem with the bridge, there is no way I could go from 1 ohm to 1 gig and then 1 gig back to 1 ohm. Now, these are all bootstrap values. So the one
yeah.
ohm is measuring the 10 ohm, 10 to
Explain
100.
that a little bit because yeah, SPC is statistical process control, but when you do your bootstrapping, you're extrapol. Yeah, you can explain this much
Yeah,
better than
so
I can.
when you're bootstrapping, what you're doing is you're taking a known value. So the known values that we have in resistors are typically 1 ohm and 10K. 10K is your break point. So you bootstrap from 1 ohm all the way up to 10K. So you take your 1 ohm resistor that you sent to NIST that is calibrated by via quantum Hall or some other type of intrinsic standard, and then you utilize that to measure your 10 ohm. Once you get your 10 ohm value, you take the newly found 10 ohm value and you go measure the 100 ohm value. And you do that until you get up to 10K. So let's forget about the 10 gig for now. So once I get to 10K, I'm taking my newly extrapolated bootstrap value and I'm saying, okay, now let's do that in reverse. So now I have a 10K value and I'm going to go measure my 1K value. I get a new value for 1K and I'm going to go measure my 100 ohm. I have a 100 ohm. I'm measuring my 10 ohm. I have a new 10 ohm value. And I'm going back to my 1 ohm. So when I did that process, I ended up exactly where I began from. So that was telling me that I don't know what you're doing differently, but the instrument is working properly. Well, this didn't sit well with the metrologist, so I ended up taking that and I sent it back to the OEM, and the OEM found a problem with it. And the
Wow.
problem was it actually had an internal guard that was I don't know, for lack of a better word, blown open for whatever reason. It was the guard was broken, and that's what was causing the problem. but they too had the problem of, well, what is the deal? I'm going from one ohm to 10K and 10K back to one ohm, and I'm seeing the same values, but it's the same values, but they were wrong because the statistics shifted. I forget which
Right.
way they shifted. They either shifted up or they shifted down, but they shifted. And there was a legitimate problem. So just because you have the right equipment, you also have to have the right personnel that's utilizing that equipment and knows what they're looking for.
Right. And this is where you just did a more recent article in Quality Magazine of data integrity and some of the pieces that we're working on together for the control chart document on how to do control charts. And it is so critical that you understand what you're putting into these. And we're going to have a lot more explanation on that with run charts and all the other charts. But the good news that the good pieces of this is if you're running that process control, you can start to catch. That's what happened right here, right? The
Yeah,
technician was running the process control, charted this and said, Greg, excuse me, but my charts are out of control, right? And
right,
then you're checking it using the bootstrapping technique and saying it looks good.
right.
So
All right.
by your standards, people continue to make measurements by using the statistical process control. It's flagged, and recalls and everything else are very. Your risk is very limited depending on when they actually call. You know what was calibrated with it between the process the process checks.
Right. And fortunately for us at the
So,
time, I mean, we had such tight statistical process control. And for those listening to this podcast that may not know this, when you implement statistical process control, you also have the ability to make an OEM spec far more accurate because you're trending
mhm,
exactly how this instrument is
yep.
performing. So the shift that we were seeing wasn't something dramatic. We're talking a shift of less than a part per million in most cases, but it was a shift nonetheless. So
Hmm.
that's what flagged the metrologist in this lab is that he knew that there was a significant in our realm shift. It didn't have any effect on any product that we were calibrating, but it was a unexpected statistical shift in our process, and that needed to be addressed. That's really what it was. But like I said, on the surface, the instrument appeared to work as advertised, but there really was a problem with it.
And some are difficult because people do not have these checks. They just rely on the manufacturer. When you are a manufacturer, you live on this. There are situations where things, regardless of how good your process control is, things can escape and people can do, that mistakes can be made, or you're not catching something. The technician, a lot of times, oh, we're using something different than what the customer used. And when we do it, here's our setup. We're using this hardened block, 44 uh, blah blah blah, and then you find out they're using aluminium or something. But yeah, it happens. I'm not saying I just want to set that preference or just setting that standard up that no one's perfect, and when we claim 95%, there's going to be things that do escape, and people do need to do the checks, even though when it comes back, us as a manufacturer. Doing the recall and doing the check is quite costly. And even if we're only wrong 1% of the time, that's still, if somebody catches that, we want to correct it. It's bad for them to keep using the instrumentation, and we keep doing things to improve and improve and improve. But I can tell you that the more cows you do, if you do, like Greg, you had it at different places. If you do make up an easy number, you do 100 cows, maybe you don't have any errors, right? If you're running a really good system. If you run 500 cows, chances are one of those is going to be bad if you're not monitoring, statistical outliers. What's the rule? The statistical outlier. It's one out of 376 or something, or 371. The outlier where
Um,
one out of every 300. I'll find it here, but go on. So
I don't recall that number off the top of my head, if you don't have that, then there's something that's going on. And there was a company that I worked at where there was a technician that did close to 1,000 calibrations, and this technician was calibrating handheld DMMs, clamp-on ammeters, M-Pro 2%, 0.2% shunts, or 2% shunts. I forget what they were. No, they were 1/4% shunts. Anyway, regardless, 1,000 calibrations, 0 failures. And I
Mhm.
found that extremely hard to believe considering the type of equipment that it was. And also, when I started looking into it, now how I caught this was I was doing interval analysis. And this is also very interesting as a find as well. The interval analysis on this one DMM that I was looking at, the all the calibrations that were performed via automation had a 92, 93% end of period reliability. However, the ones that were calibrated via um, a human doing the calibrations, zero. There was zero out of tolerances.
So
So
the
that
human's
kind of
better than the automation.
right, and the thing is that there's reasons people do that, and they're not the right reasons. But the reasons is, well, if it's out of tolerance, well, now I have to adjust it. Now I have to take as left data. So being that it was a manual process, I'm just assuming the process was this is out of tolerance. I'm adjusting it, and this is the way it is, and it goes out the door, and I'm going to flag it as being intolerance. That's what my I suspected was going on, because the problem with the high reliability items were only on manual pieces of equipment that were calibrated. Anything that was calibrated via automated means had what I was expecting to see, which we were saying that we ran at 95% end of period reliability on all of our standards. And that kind of proved it on the automation side, but on the manual side, that did not reflect that adequately.
Yeah.
And as I
It's
started digging into different technicians, I was able to see through the numbers that who was actually calling these things out of tolerance and doing the proper thing. But it was interesting that you're able to find so much information by just looking at some of the data and
mhm.
filtering through it.
Yeah, it's one out of three every 387 measurements.
387. Okay.
When I was in taking the Six Sigma, the green belt, I did black belt and whatnot. When I was doing the green belt, everything we were doing was about scrubbing data almost. It was like, let's take this data, let's launch catapults and everything else. And then you just see like the class, we'd all take 10 measurements and there were like 12 of us. And you would just see like these random outliers, right? And you've done a lot with interquartile range and all that, and you can spot them. We have automation checks, we have everything else, but the typical instrument that's submitted to us, maybe we're doing 33 measurements on. So just rough math, that's like 1 out of 12 instruments is probably going to have a bump in the data that we can't explain. Luckily, we're doing enough measurements, technicians are watching it. Though my point is, and I talked to NIST, is even at 95% confidence or whatever, there's still that tendency where things can escape the lab that are, and people need to be checking your work. You need to have some type of check system in place before and after things go out, some system to maintain it and do it. I'd be so much happier because you know what that would mean? If they have a really robust check system, that means that less stuff's coming back, right? Because
Right.
only the stuff that's failing. Right now, more stuff comes back because it's easier a lot of times. And I think other labs probably operate the same way. It's easier to double check it than to go through all the troubleshooting, depending on what that troubleshooting is. And that's what I'm really getting at. And then your system, because it costs you when you lose that equipment for a while. When I say it's the PETA fee, I'm not, I never want to bash any customer or anything like that, but it really, it hurts both the customer and the organization when people do not have process controls and statistical checks in place because you're
Right.
doing work that you don't need to do. And even if the company you're working with is kind enough to take everything back at no charge, it's still, you've sent that for Cal, you're out 2 weeks, and now they're going to do it. Even if they expedite it, you're out another week, and that's money you could be earning on that equipment. So there's justification everywhere to put in some type of sanity checks, process controls, whatever you want to call them. I'd prefer that everybody do SPC, statistical process controls. That is more of a pain in the butt for them though, Greg, because you're till you even get started, you're looking at 7 different subgroups with at least 3 measurements to start your control charts and have valid data, some valid data.
Okay, so a little backstory on that. The use of check standards.
Yep.
So regarding the resistance bridge, we only sent two Thomas 1 ohms to NIST, and we only sent one SR 104 to NIST. SR 104 is a 10K reference standard, and the Thomas 1 ohms are obviously the 1 ohm reference standards, but I had 3 additional Thomas 1 ohms that were identical make model. They were LNNs. So what I would do is I would have a design that would do an inner comparison between them as a check standard to make sure that I knew that that value that I got from NIST was being transferred all the way up to my 10K standard. And I also had a spare SR 104 that I utilized when I got back from NIST as a check standard to make sure, okay, my Thomas 1 ohms are running good at 1 ohm, and I know my SR 104s are running good at 10K. So by having those under tight statistical process control, I can make the assumption that everything in between those values is also running well.
Yeah,
So I mean, I can't say enough good things about having statistical process controls and check standards to make sure that your processes are indeed in check, and that you're not living in a bubble, you're not making measurements in a vacuum, you are getting external numbers and making sure.
it just started. Like so as we're winding down, it's like it's what we started with, not the band conversation on albums, but what we started with TUR is is going to end with that is and buying the right equipment is buy the check standards, right? If you're
Right.
going to invest in high quality equipment, invest in high quality check standards to make sure that you have something keeping everything in line. You can run production lots or you can run all your calibrations and chart those. That will give you a lot of insight into your process, though you still should have that check standard that if you think something's going a little bit awry or something else, that you can stick that check standard in and say, no, it's everything's good. Or yes, it is getting higher or no. Because chances are when your other situation that was like 24 to 1 TUR, 25 to 1 TUR, whatever it was, chances are that's on what they want to measure. If they get a really good check standard, that ratio is probably going to drop quite a bit, right? I mean,
Yeah.
yeah, yeah. And
Yeah.
then it's like, okay, but it's all about propagating your risk. And if you do it correctly, the time that you invest in it is going to save you lots of headache and lots of money. And quit being, I'm going to make a comment of saying quit being lazy, but some people, it's not a laziness. Some people just don't know how to do it. I know from a fact we struggled with it for so long. It's getting meaningful data, and that's where you can read Greg's paper and quality on data integrity and everything else. What else do you have? What else do you have, Greg, on as we're wrapping down for people?
That's all that I've got on on this particular one. I will say this on data integrity. The reason that I wrote the paper is because I see a lot of different laboratories, and what they do is they'll take repeatability data and they just take it without any regard to, is the data even good? Does it even make sense? They'll take a series of 10, 20, maybe even
Mhm.
30 measurements and say, okay, well, that's my repeatability. But when they put 2 technicians on, and I had seen this firsthand, you had one technician that had a group of data set that was here, and the other technician on the same piece of equipment had a different data set. So when you do ANOVA, which is analysis of variance on it,
Yep.
this test, the data failed the F critical test, and F critical, for those that don't know what that is, it's, you could think of it as a single-sided tolerance. That when you do all the math that goes in the back of it, you have an absolute line in the sand, and as long as your data is less than your F critical value, that means that your data is homogeneous, and you can accept the null hypothesis, which means yes, my data is homogeneous, it belongs in the group.
Right.
There's another statistical test that's run in the background too, and it's called the Ramirez-Runger test, and it is time dependent, meaning that I make measurement one, I make measurement two, I make measurement three, and it does some math, and it gives you a number that says this is the probability that your data is going to fit any distribution. I had a client that had taken repeatability data, and that test came back as zero, meaning that there is zero probability that it's going to fit any kind of a statistical distribution at all. It failed the F test, the p-value was zero, and this particular client decided to go ahead and run with it and say it was good, even though I said, you've got a problem with your process. And their answer was, well, it's good enough for us. We really don't want to dig any further, but it failed every statistical test that there was. But I see some labs doing this because they don't understand it. They don't understand what it means, but it really gives you a good insight into what your processes are if you take the time before you start doing uncertainty analysis. Just look at the data you're taking. Does
Right.
it make sense? So
And then
that's
put uncertain, yeah, and then look at some uncertainty too as well, because you can. I have number of measurements that fail the F test, and you know why they fail? You know why? Because the standard deviation of the measurements, it basically shows that there's such tight agreement with the numbers, and then you move it to another machine, and it says, oh, it's different. But you have to look at your numbers and say, wow, my difference is 15 parts per million, and we're claiming 16 to 20. You're saying that's not too bad, but the F test sometimes will fail in that situation, and that's something that we need to explain some more in the paper where it's or not paper that in our document that we're working on. Uh, you know what I mean, Greg,
right,
as
right,
far as that. Generally, what I interrupted on that one because maybe people are looking at things for the general population. You should have like an agreement and say, look at the p-value, look at the F test, look at everything else, and how good your data. If
right,
you want to step back from this, and typically if you have something that repeats really, really well, like we were looking at the 6 decimal place and the latest one we ran, it had 300,000 counts of resolution at the 6 decimal place. And we were within 2 counts and it failed the F test. Well, 2 counts out of 300,000, right? Just rough multiplication. That's about 7.5 parts per million difference, right? Between the two tests. But it was the repeatability did not have that dispersion, that large spread of data, that it was so tight that it said, look, your F values. I'm looking at this, and then I was like, I run Monte Carlo, and in the end, we were about Monte Carlo simulated the other ways you can do it. Monte Carlo simulated 120,000 runs, and in the end, we were like I think it was like 7.5 parts per million. It was some number like that we had
right,
agreement, but it failed. The F calculated test failed. I'll have to show you that data, but I don't want to scare anybody because it is a good test. It's just look at what you're measuring, and you have to somewhat compare your machines, right? So you
right,
have to, after you do put the uncertainty around, well, how good am I claiming to make a measurement? Well, between machines, I have variation of 7.5 parts per million, but we're claiming that we're 20 parts per million. What do you do there? And that's what we're hoping to answer in a lot of our in setting looking at that uncertainty and setting additional limits on your control charts based on
right,
your overall uncertainty.
right.
So, but yeah, I shouldn't have interrupted that because I'm in a rare case that probably very few people see. NIST may see that, I would imagine, between some of the stuff that they do, that it's that critical and their measurements
Well,
need to
and,
stand.
and there's another part too, and I don't want to take up too much time on this subject, but I mentioned bootstrapping resistors. Well, there's another statistical test, and it's called bootstrapping also, but it's something a little bit different. Like in your case, it's expensive to get data
Mm,
because of all the runs that you have to do and account for all the different errors. It's very expensive. So there is a statistical method that we could outline in the paper called bootstrapping, to where you take a group of measurements that, let's just say, that is very expensive to get the data, and all you have is 10 measurements. Well, you could take those same 10 measurements and keep resampling those
Yep.
with replacement, and you end up getting what looks like a normal type of a distribution to help you get a better understanding about what
Hmm.
your data looks like. But
Hmm.
that's a deep topic for another discussion. But there are so many ways that you can get um, your systems to be verified and have high confidence in them by using a few simple statistical tests.
Yeah, just start it. Get check standards. I guess the first step is if you don't have them, is go look what kind of check standards are available and just start to figure out how you use those check standards properly. Hopefully, talk to the manufacturer. Some people have better published documents than others, as we
Right.
know that Greg has been through, and figure out like a way to just start taking these measurements and looking at what's going on, and from there you can kind of determine as well if you have the right. Well, before you even do that, you can determine if you have the right equipment by doing the TUR calculations. They're going to give you a lot of information on if you know them and the risk-based stuff, Greg. And how do they? What's a great tool for them? Do they just contact you? We're getting to the point where this starts becoming more complicated. If they start making the measurements, they get the reliability. They have a lot of stuff to do. Is the best thing if they don't know is to kind of contact you and start them on the path?
Oh, sure. I could start them on the correct path. If anybody's got some questions on that, I'd be more than happy to help anyone out to understand these topics because they are significantly more involved than a 1 hour podcast.
Yeah, I was trying to get into it where they can do it, but the start of the check standard and the start of actually looking at things and seeing, because they're not going to know. I mean, they might go look up TUR, and if you go look it up, you're going to find a ton of information on it. The best thing I can say with that is there's definitions, there's guidance out there. Read our decision rules at MH Force. IndySoft probably has IndySoft shares it. MH Force, we have it on our website.
Yeah, we
That
share that. Yeah.
that document took us a lot of time, and that's a good overview document. It is at the intermediate level, so there's going to be the retention of everything. If you're new to this, it's simpler than most stuff that's out there. I would like to say it's simpler than all the stuff that's out there, Greg. I don't know if it is or isn't if we talk about that, but it is simpler. And then if you at least have some basic knowledge of what's going on, maybe you can formulate some better questions for Greg and then start that. See if it makes sense. Because once somebody starts you with their process, the cool thing about the consulting gig and everything else is once you get people set up, they can just keep making this measurement until they want to work on something else or need some hand holding elsewhere. Uh, it's virtually pretty contained until something happens, and then of course it's like learning along the way, right, and figuring it out. So give
Right.
them your contact info. Greg Cenker at
indiesoft.com for anything that's indiesoft related. For anything that is consulting related, it's gsenker at euclideanengineering.com. So anything indiesoft related, I'd be more than happy to help any clients, anything that requires in-depth understanding of some of these more advanced statistical concepts. It's gsenker at euclideanengineering.com. I'll be more than happy to help you.
and you're also on LinkedIn if it's
And I'm on
easier. You
LinkedIn.
just look for the
Greg
guy
Senk.
that Greg
Yep.
Cenker at IndieSoft. There's only one at IndieSoft, and it's clear on his LinkedIn profile. And you can bother him that way too. Tagging him
Of
in some
course.
posts that tagging him in some guitar post or some other post on anything.
That'll get my attention. And then it's like, oh, I got sucked into this.
Yeah, like knife sharpening. Greg takes it to the nth degree. Like even knife sharpening and everything else he uses. See, yeah, it's
Oh, yeah, I've got a geek knife sharpener, and I even use an inclinometer to make sure that I'm getting the same angle on both sides of the blade, and I take it
and
to
this is
that
just
level.
and this is just to cut up produce, steak, or whatever you're eating too. This is
Exactly.
nothing more than if people think, oh my, you're a skilled knife thrower or whatever.
Well,
No, it's not
see,
that.
but that has that added benefit, and the benefit is that once you do that, then you can just simply take a sharpening steel and redress the edge, and you're fine. But it's getting that initial edge that takes that takes the skill. So
Yep.
once you get that done, then it's pretty easy to maintain it.
No, awesome. Hey, Greg, thanks. And if those want to check out more, learn more about Greg through his years, there's also the Metrology Today podcast where Greg was on talking about all his history and everything else. And everybody check out the decision rules document. Check out IndySoft if you want something that's super easy to implement some of this stuff, TUR and the other things. Greg and the group, all of them have a great software package that's probably easier than going it alone and investing all the money with everybody else. And they have IndySoft has a pretty large market share overall, and some really great people, seasoned metrologists and
Well,
other.
we have staff metrologists that are, my job and Mike Lynn's and Will Twentyman's specifically to make our uncertainties and our metrology aspect of it. Besides being an asset management piece of software, it's to make the metrology aspect of it extremely accurate and user friendly. That's
Yeah, that's the big one because it gets complicated. Though you're gonna hate me for this, Greg. You're not gonna hate me for this, but you still should know something about it.
yes.
Because too many people just want handed over the keys, right, without any explanation of what this light switch does, or that does, or this does, and everything else. And then they fuddle, and fuddling's not the best. So there's still reading documentation, learning as much as possible is still highly encouraged. And then guess what? If you're educated, chances are you're going to go to an IndySoft or something very similar anyway, because it's just going to make life easier to manage all your assets and do your cows and everything else. So,
Right.
all right, thanks, Greg.
Well, Henry, thank you so much for hosting this. Much appreciated. Bye, everyone. I hope that you took something valuable away from this. I'm sure we'll be doing this again in the future.
Yep.
All right. Thanks, Henry.